then I'm going to hand it over to Brandon. So just quickly to start, what do we do at Tangram Vision? Well, most people know us for calibration, and that is sort of the bread and butter of what we do. We have different ways we do that. We have two calibration systems. We have Metrical, which is our bundle adjustment tool that does camera, LiDAR, IMUs, depth sensors, and very soon radar and 2D LiDAR. We have AutoCal, which does online calibration of cameras, depth sensors, and IMUs now, and very soon we'll be adding, again, LiDAR, radar. We launched a depth sensor that is self-calibrating as well as AI-enabled called Hi-Fi. We'll talk a little bit more about that in a second. And then we also do periodically consulting for perception and sensors. Just a quick note on Hi-Fi. It's available for pre-order right now. It'll be shipping within a couple of months. And we feel like it's one of the best depth sensors available today for mobile robotics and pick-and-place robotics. It has very high resolution optics, lots of onboard AI compute, and just a lot of nice usability features that our customers have been asking us for in a depth sensor. We pride ourselves on trying to provide education and resources to the perception community. You may be familiar with our blog. If you're not, we definitely recommend going to tangramvision.com and visiting our blog. We have over 70 articles and tutorials about calibration and perception. We also have tools like our depth sensor visualizer that helps you compare range and field of view of popular depth sensor models. We'll be launching a LiDAR version of this very soon. We contribute open source software and tools, mostly in the world of Rust. And as a side note, if you're interested in chatting about Rust, we're huge advocates. We'd be happy to chat about that. We feel strongly that it has a big role to play in robotics now and in the future. And then lastly, we actually wrote a book on calibration. It's free online as a PDF. You can actually also now order it on Amazon.com. So with that said, I'm going to hand it over to Brandon. He's going to talk about Metrical, and then he will go into a demo.
Awesome. Hi, everybody. If you don't know me, I'm Brandon. I'm the founder and CEO. We are very excited to get the new version of Metrical out, especially because it has a lot of usability features that we've been really wanting to put in. For instance, now we've gotten to the software to the point where you can render everything all at once. So that includes components, the calibration, and then the object space as well. So one of the earliest claims we made is that Metrical can figure out all the targets and correct not just your system, but your environment as well. And here you can see in that GIF, we're doing just that. I think this is 18 boards, and we have corrected or rectified all of them. So really exciting stuff on the rendering front, but also really exciting new additions to components. So now we do IMU intrinsics as well as extrinsics. That includes scale, shear, rotation, and G sensitivity. That's all in the documentation at docs.tangramvision.com. We also now support omnidirectional camera models, which is more for catadioptric cameras, basically camera mirror systems that allow you to see 360 degrees. So if you have a extremely wide field of view lens, now you can just use Metrical for that too. No need to go to another calibration source. So we have, as of recording, 8 different camera models for any of your camera needs. Really excited about that. We also have improved our LiDAR data input filtering and upgraded to Rerun 0.14. Rerun is the program we use for rendering. That kind of came with all the rendering improvements. So yeah, just a lot of usability and feature additions that just strengthening Metrical. And we're already getting ready for the next version coming out. So look forward to that as well. Cool.
Cool.
Should we just
Right.
roll right into it?
Yeah, I'm going to stop sharing my screen and I'm going to transfer control over to you so that you can.
Perfect. All right. So today's webinar is
Hello,
about
Brandon?
camera LiDAR. We covered, if you were here for the webinar last month, we covered camera in the form of a RealSense calibration. So basically understanding what it took to get good camera features, good camera data, and then put the data through Metrical, which was the smallest part of the whole webinar, and then flash it onto here. We're not going to do any flashing today because now we're multimodal. We're going between cameras and LiDARs. However, we will still go through all the steps before, understanding what makes a good calibration data set for camera LiDAR, understanding the gotchas in these different modalities and how Metrical deals with those, and then again, putting it through Metrical and seeing how the results come out. And again, you'll find that processing Metrical is actually the shortest part of this whole webinar because it just does it that fast. But anyway, let me share my screen quickly. We'll see kind of a preview of what we'll be going over today. Can you see my screen now? Cool. So what this will be up soon, is a new tutorial on docs.tangramvision.com. You'll see this is a local host. This is a development branch. We have tutorials every time we run a webinar. We're both going to record that, put it on YouTube, but also provide the tutorial in the docs so that you can just reference this on your own. Calibrating camera LiDAR. This will go basically over exactly what we did today. We'll discuss the target, discuss data pitfalls, and then actually running it through Metrical. So I'm sorry it's not up quite yet, but it will be up by end of day. So make sure to look through that. And then the data set we'll be using today will also be in the Metrical sensor calibration utilities repository. So literally everything we do today will be replicated for you. And now let's go to the real stuff. I'm going to not share my screen yet because there's a little bit of explanation I need to do for how Metrical operates. This is the circle board. You've probably seen, well, I don't know if you've probably seen this, but if you've ever been on a video call with me, it probably sits behind there on my piano. And so what the circle board gives Metrical is a way to associate camera space, which is a projection of 3D Euclidean space onto a flat surface, and 3D space, which is what the LiDAR natively gives, right? And so we have these two different modalities that don't necessarily correlate, that we have to bridge. And the way Metrical does it with its target. So the target is literally just a square Truco board cut into a circle, centered in the center of the Truco board. And then we put retroreflective tape on the edges. So what this does is gives us a way to correlate the center of the the center of the marker board, which is what you would usually find with a camera space, and the center of the geometric circle made by this retroreflective tape, which will turn out very brightly in LiDAR. So when we are first thinking of ways to kind of approach camera LiDAR, we try to be a little too clever with it by taking fiducials, that would be corners or, rectangles, or just matching different features in space. But what we ultimately found that was for a production line calibration, you really don't need any of that. Metrical is designed to give you, solid ground truth results. And really, you don't need anything found in nature to get that done. You need something that is very distinct. And so the camera, or the circle, kind of hits all those marks. You're not going to find big retroreflective rings in nature. It comes out very brightly on LiDAR, and the signal is always strong. However, that being said, as we go into the data, we'll see how that signal can waver. Some LiDAR brands, specifically Ouster, I don't know if this is their firmware or their hardware, and I'm not saying ouster LiDARs are bad at all. I want to say that very clearly. But with the retroreflective tape, sometimes you'll see that the set of points reflecting off the retroreflective tape is not in a plane. So it'll actually be a little bit of noise or a little bit of bloom on the edges. And Metrical can actually deal with this. So when we derive our object space, which is what we send to Metrical to describe the circle dimensions, there's a flag there that's called detect interior points. And what that says is, I want to use all the points on the board for calibration. What we can do in the set of a noisy LiDAR is actually turn that off. So instead of using all the interior points for calibration, all we use is what's on the retroreflective tape. And we found that just that little modification allows for much more confident calibrations on the other end. So even if the moral of the story is, even if you have a noisy LiDAR, we can deal with it. So that's the board. You don't have to have a certain size. You don't have to have a certain fiducial. It just needs to follow the pattern of centered marker board, centered circle. And as long as you have that down, Metrical can deal with it. And so now we can see how you can describe that to Metrical in the object space. And I'll share my screen now. Here we go. So today, what we're going to be looking into is a data set with 2 cameras and a LiveVox. Now, a LiveVox doesn't have a sweeping beam motion like a Velodyne or a spinning LiDAR. Instead, it has kind of a sweeping pattern. It almost looks like a flower, and we'll see that a little later. To Metrical, this doesn't make a difference. There's no ring counting or alignment using rings in Metrical. Instead, it's all about the retroreflective tape, right? As long as we have that strong signal, we can align. So that's to say, it doesn't matter what pattern your LiDAR is giving you, we can deal with it. But let's look at the object space for this file, and we can kind of dig into what that means. Demo camera LiveVox, object circle.json. So here's my object space. And usually when you're describing the object space to Metrical, it's
it looks like Brandon is frozen. I'm going to message him.
modalities together. Am I back?
You're back.
Okay. Did we get the board, regular board? Oh,
we did
Adam,
not.
I can't quite.
Yeah, sorry, I muted myself. We did not. Please cover that.
Okay, there we go. So let me do that again. Sorry about that. What I was saying is, you can see the object space, Jason, Adam, just to make sure. Perfect. So usually when we describe object spaces to Metrical, it's very straightforward. What we're saying is we have a board, say it's a marker board, and all we have to tell Metrical is the dimensions, and it figures everything else out, right? You just say this squares this dimension, this squares this dimension. I have so many squares in the line. That's fine. However, with circles, what we're doing is melding 2 detectors together. So we have a 3D detector for LiDAR and then a 2D detector for the board. And so the way we tell Metrical that these are one and the same is actually through this concept of a mutual construction group. Every object space has a unique identifier, a UUID. And so you can see object space 1, 2, 4, 3, B, da, ba, 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 ba. This is our marker board, and we've given it these dimensions. Object space 2 is the retroreflective tape, which we describe as a circle, and it has these dimensions. And here we're saying, please use the interior points for detection. In the object space, if we separated these out, they wouldn't be related to each other, and there'd be no way to tell Metrical that these are one and the same. Mutual construction groups do that. We just put them into the same array and bundle them in. Now we're good to go. So it's just one more step of complexity, but all of these object-space JSON files are also in the Metrical utilities repo, and you can just copy paste. Easy enough. That's what I would recommend. So once we get in those right dimensions, that's all the setup we need other than our data, and Metrical does the rest. So here we have, my demo camera Livebox MCAP that I'm going to be working through. We're going to see that in a little bit. I'm using my object space circle that we just described, and I'm setting my models for the LiDAR and camera to be no offset, so the default LiDAR model, and then using OpenCV's default camera model, RAD10, for the calibration. Now, a little bit on data intake. When we use the camera LiDAR board, your first instinct might be to just kind of move here and there and up and down, kind of like what you would with a camera, or kind of like what you would do with any calibration. But in fact, just like a camera board, it does help to rotate the board in the kind of Z forward axis, I suppose. Because what you're looking for is to get rid of ambiguities, just like you would in any other system, get rid of ambiguities in the camera frame. So even though it doesn't quite matter for the LiDAR is just finding a circle. For camera LiDAR extrinsics, it's still encouraged to rotate your board if you can, right? And so angles, distance, rotation, all are necessary for a good calibration data set, even for camera LiDAR. Okay, so we have all that. This is literally all we'll need to write to process the camera LiDAR. And so let's look into it. I processed it before the call just for demo safety. You know how that is. But you can see that this still moved very fast, and I've timed it to prove the point. Let's see. So we first ran the init command, which looked through our data set, found a initialization of our calibration. It wasn't perfect, but it gives us enough timing and space constraints to get started. And that ran in 28 seconds. The calibration command, which actually does the calibration and filtering, ran in, I think, 2 minutes. 2 minutes and 31 seconds. And that was with rendering calibration applied. So you can see that for this set of LiDAR and 2 cameras, the whole process end to end with rendering is done in about 3 minutes. And you can make that much faster if you automate this process. So again, kind of proving the point that Metrical really gets the stuff done. Once we have our initialized model, we can move on to calibration. And there are only a few things I want to highlight here. Just as our camera data set that we did last webinar had filtered frames, this camera LiDAR also benefits from motion filtering. And so we've left motion filtering on for this data set, and you can tell it's had a huge impact. Out of the 2,700 frames for each camera, only about 90 were used. And then from that, only about 45 were detected. So we've gone from using 2,700 frames to 45 frames, all of which we know are good data set or good data for calibration purposes, right? And so this is really going to make our process more efficient, and it's done automatically for you. You don't even have to think about it. We can see that for this data set, the detections were heavily weighted into the center of the image. They get a little far out to the edges, so this is not a bad data set, but it's not great either. I know for a fact that this camera doesn't have a lot of distortion, and so the later results that we're going to get would be comfortable for me. However, if this was a wide field of view lens, something greater than 100 degrees field of view, for instance, I would second guess these detections and want to do it again, right? But again, the fact that Metrical gives you this before you even calibrate is an invaluable source of information. So you have that going in. Here's our timeline. We've rendered the LiveVox data and the cameras on the same timeline, so you can see that, there should be synced pairs between all of these observations going forward. Good, we didn't mess up any timestamps. And then after all of our pre-processing is done, we just go into the initial adjustment. It's done in 5 iterations. This is a very tight data set. We derive outliers for just cameras. I don't think we have any LiDAR outliers. And then reweighted adjustment in 5 iterations. So super fast. And this is the story for most camera LiDAR. Usually camera initialization, if you have too many of those, will actually be the longest part of this. And then the actual camera and LiDAR adjustment will be pretty fast. So all that is to say, everything happened very, very quickly. We got binned reprojection errors. These are all looking really good. Though you can tell at the edge of the image, we're in the yellow. We're getting to a little higher reprojection. And again, what I would want to see from this to improve these results would be more features at the edge of the image, which I think would then fit the model a bit more precisely going forward. But again, for our purposes, this is looking really good, and I think we can use it for camera LiDAR alignment, no problem. Here's our OpenCV distortion and projection, along with some covariance standard deviation values, which tell us we're pretty certain about these going forward. And then here are the calibrated extrinsics. This doesn't mean a lot to you right now. It can be a little abstract, but we'll render these later, and it'll make a lot more sense. 2 things I want to highlight from the summary statistics are unique to camera LiDAR. What you're going to get, aside from just reprojection RMSE, is these 2 boxes down here, circle misalignment RMSE and interior point RMSE. And these are unique to camera LiDAR pairs. And these are going to be amalgamated out of every camera LiDAR pair in the set. So going back to our circle board, the circle misalignment RMSE is not quite what you would expect. It's not the full circle, but rather the center of the circle. What we're looking at is the misalignment between the geometric center of the circle in LiDAR space and the center of the board in camera space. And so this is why it's important that when manufacturing a circle, if you do this at home, you want to make sure that the circle cutout for the board is centered directly on the pattern, because that's actually a metric we rely on. So you can see in this corrected data set, we're about 3 centimeters off in the middle, which would be about right here, maybe. That's not horrible. That's not bad. There are probably some things we could have done to take this data set a little better and make that more resolute. But understand that if you print this off-center, off-sides a little bit, that error will always be high, right? And this is just something Metrical uses. The interior point RMSE is going to be the layer of points in the interior fit to the plane. And so that is what we were saying, like maybe it's not worth it if your LiDAR has too much noise, because then what you're fitting is just a bunch of noisy points to a plane, and that's not really going to give you a tight fit. So in the sense where we get a noisy LiDAR, we usually just cut that out altogether. You can see here, I set that flag to true in the object space, and we got a value, and it's a really good value, which is telling us that this LiDAR, can be trusted. But for noisy LiDAR, just shut it off. Don't worry about it, and you're still going to get good alignment results. Cool. So those are all our results. That's kind of all the exciting stuff for here. But now let's go to the actual rendered result, which is usually intuitively what you would want to see first in a camera LiDAR calibration. You want to see that alignment. You want to see it's crisp. So again, we're using rerun, and this is revamped for version 9.0. Adam, can you see my screen once more?
Yep, I can see it.
Perfect. So again, I rendered this before for safety purposes on demo, but it's going to render as you calibrate. So if you set the flag for rendering, the -V flag, and calibrate, make sure you have an instance of rerun running at the same time so that you get all these messages. Otherwise, the messages will just drop because it acts like a server connection. So let's look into it. The first things we would have gotten from this data set were the detections. And what we'll see is that a couple of modalities. We'll see our camera detections here in the form of these points on the grid. And the grid is colored in a rainbow, so you can kind of always see the orientation going through. But on the other hand, we actually have detections in LiDAR as well. And so every detection in the circle will be highlighted here on the side under the detection bar. And you can see the detections as they evolve in space. So this is our circle. This is our retroreflective tape. And all of our metrics will be derived from this. Again, the orientation doesn't really matter as long as the detector finds it. What the orientation matters for is the camera side, and so the camera LiDAR match will erase ambiguity, right? But this looks very detected. This looks really good. And as you can see, even though the LiVox has this crazy flower pattern going on, not like a sweeping LiDAR at all, we were able to detect it fine. So that's why we opted for the circle board instead of anything else, is for these wild, wacky cases. So our detections look good. We have detections throughout. Now let's move to our corrections. How did this apply to our data set, and what did it look like? At the end of every Metrical run, you'll be able to see the optimized poses for all of our boards. We're only using one board, and it's a circle board. You can see from this rendering. Not too much exciting here. But if we were to use multiple boards, you'd be able to see their relation in space, which is very helpful for debugging purposes. Sometimes if you use too many boards, there can be overlapping IDs, which get really confusing. We've seen that before. Or you've modified the object space to have too tight or too loose covariances, which can kind of also make the object space go crazy. Defaults are usually fine. We haven't seen any too big mess ups with defaults. But if you're doing something more custom, it's good to know how these changes affect object space. And so now it's really easy to find that out. But again, for our purposes today, it's kind of boring. It's just a circle. The correction frame here under correction is actually, kind of what we want to look at. So here we've rendered almost in a sensor fusion base all of our modalities. So we have the LiVox versus our two RealSense cameras. If we double click on the LiVox, all it does is give us the point cloud, obviously. But if we double click on one of these cameras under correction, what it does is zoom in and show us kind of the alignment between the image and the LiDAR, right? Which is exactly what we want to see. So now if I turn off, since both of these images are kind of supersets of one another, or supersede one another because they're right next to each other, we can actually turn one off here by using the toggle visibility and just focus on one or the other. So now we're just focusing on the RS1 Infra2 right camera, I think. So if we move forward in space, we can see the LiDAR spinning around, and here comes our target.
It looks like Brandon has frozen for the second time.
Horrible. Hey,
Brandon,
we're back.
Right. Yep.
I'm back. Yeah.
All right. Could you go back to when you mentioned which camera? I think it's the RealSense camera.
So I was saying, we've taken away the RealSense Infra 1, which I think was left, and now we're looking at Infra 2, which I think is right. So left and right eyes. And now if we double clicked on that, we can see the registration. And here we can go forward and actually visualize what this would look like in a data set, right? In this data set. As you recall, our metrics before had circle misalignment RMSE of about 3 centimeters. Sure enough, looking at this frame, I would say that's about 3 centimeters off. That makes sense. So what that says to me is, depending on your system, this could be completely fine. This could be all you need, right? or you might need some tweaking to get a little bit better data. Metrical is only as good as its data. I'll say that again and again. It's kind of why we focus on data collection at the beginning of this webinar. And so, some things we could have improved in this data set would be maybe standing still for a little bit longer, doing more angles, getting more features, something along those lines, right? Standing still would probably do really good because we had the motion filter on, as you'll recall. So if too many frames are filtered out, can mess with the results. I actually don't think that was the case here. I think most likely it's having to do with maybe the live axis crazy pattern versus the motion. So there are more factors here. But regardless, this is not a bad calibration. And for your set, and for your system, this might be satisfactory. It's really up to you what that threshold is. And we usually work with customers directly to find that out. One of the first questions we always get is, how accurate is your system? And our direct response is a bunch of things. How accurate is your target? What are the requirements of your system? What do you need it to be? Because there's always a way to hit it. It's just a matter of how much work you want to put in.
Brandon, we have a question,
which
is, would putting a notch in the reflective tape be useful to establish orientation in the LiDAR frame?
Not necessarily. It could be, right? But the way we do this right now is from a full circle detection. And the reason the notch might not be useful is because you don't always have a sweep like a live ox LiDAR. You could have a very sparse LiDAR going through. I'm thinking of a VLP-16, which was one of the motivations for this circle in the first place. So unless you had a very specific reflective tape pattern that is always detectable, and unambiguous in that LiDAR frame, you could just be confusing your tests, right? And so we've kind of hit a happy medium between constructability and detectability with the circle target. And so far, the ambiguity hasn't been extreme. I will say one thing I skipped over on that point is that in addition to defining the center and the radius of this circle, two other things that we look for in an object space are the X and Y offset from the geometric top left of the marker board. And so what that means is, if this marker board was still a rectangle or a square or whatever it is, and you could see the top left corner, how far would that top left corner be from the center of the geometric circle? And so by programming that in, we actually get rid of a lot of ambiguity already, because the camera gives us the orientation and the ring gives us the position in space, right? And so we've kind of built that in already. But suffice to say, I think we've hit the medium between the sweet spot between what we would want here. And so that's the gist. Like I said, running Metrical is just 2 lines of code. All we had to do is get the data and kind of describe the object space, and the object space is written for you. So it's a very quick and clean calibration job. This same process would apply to as many cameras and LiDARs as you want. So one of the things that we might need to discuss, I mean, it's good to discuss here because it does come up, is that having a lot of cameras and LiDARs beyond 2 and 1 of each, you can get into scenarios where it's just hard to get all that data logistically. You can have a camera mounted, 3 meters above you, and then a LiDAR sweeping over here, and you still need those calibrated, right? And so in that case, in these larger multimodality settings, you can actually seed a calibration or pipeline a calibration through. Metrical pipeline is a mode. It actually allows you to go calibration 1, calibration 2, calibration 3, and actually move results through the pipeline so that you don't drop those precious covariances that you've derived before, which tell you a lot about your system. But you can actually use them in the next step of a calibration. So when this happens, we usually advise customers to just run their intrinsic model, get in Metrical, get that going, and then pipe those intrinsics directly into a larger extrinsics bundle adjustment. All that being said, we always advocate for doing everything at once because that gives you the best idea of the accuracy and precision of your system. Always, hands down. So, and it also just cuts down on time, right? If you can get everything at once, go for it. So if that doesn't work, there's flexibility embedded, but hopefully it does for you and you always get good results.
Cool. So in the time that we have left, we're happy to take some questions. We already have some. Brandon, I don't know if you can see, I've assigned a couple to you, and we'll continue to take them after we answer these.
Man, I'm sorry my internet keeps cutting out. That happened last time too. Never does any time else. But Adam, did I cover everything that I might have skipped over?
Yeah, I think you did.
Okay, great.
So, well, maybe just to get to the questions, the first question is, where do you get the role of the two sensors relative to each other?
So talking about roll, pitch, yaw, that's probably for two camera LiDAR, it comes down to, so the two camera LiDAR is just using the camera to detect the center of the circle and then understanding from the angles involved and the distance involved how those match up in geometric space. That's it. It just kind of shakes out because even though the camera is a continuous circle in the plane, the fact that you can adjust it in all 3 or 6 degrees of freedom with the camera detecting its side of things allows for tight adjustment. So
cool. Next question. What quantitative metrics other than reprojection error does Metrical provide?
Glad you asked. So if you go to docs.tangram.com, and I will share my screen here as well. Let's share my screen one more time. So if you go to talks.tangramvision.com and go to Metrical intro, what you'll see is a results tab on the left. Click that, and it'll give you a breakdown of the console log, which is everything that we've kind of discussed on the side. Very detailed discussion about the console and the results JSON, which is actually the output of Metrical. So everything that you see is kind of a easy digest of the results. The results JSON itself is incredibly dense, and anything you would want to calculate, you can probably do here. But even beyond that, we have a ton of residual metrics that we provide for all of these modalities. Here's an explanation of circle misalignment. There's composed relative extrinsics for components versus the object space, imagery projection, obviously, but then, things for IMU, things for camera LiDAR, things for LiDAR, things for IMU. All of these results are always output by Metrical, and Metrical does this automatically depending on what modality it sees, right? And so if there's something we're missing, please let us know, but we try and be incredibly comprehensive to the point of it's probably too much data for most people. These Metrical results JSONs get incredibly dense. But the full schema, again, are at the Metrical utilities repository. And we encourage you to go through that, check it out, play around with the data, and let us know if there's something missing, for sure.
Brandon, can you cut and paste that URL into the Q&A or the chat?
For the Metrical? Yeah.
Yes. Another question, I can answer this one. Where can I get the circle target for camera LiDAR? 2 sources. We, as just a service to our customers, we will make one and send it to you at our cost without markup. Alternatively, in our docs, you can find instructions on how to construct that target. It's pretty simple. You don't need a super flat substrate like aluminum or glass. We usually print these on foam core. If there's curvature, that's fine. And you can order retroreflective tape from Amazon or any other source. and just put a ring of tape on the outside, and that's sufficient. When we manufacture them, we die cut the retroreflective tape just to make it look neater, but that's not totally necessary.
Yeah, you can actually see in this, in the Metrical rendering that I had up, and I'll share my screen one more time. You can see that this is very much not die cut. This is just Devin putting tape on the edges, but it works completely fine, right? As long as you have all the way covered to the edge, that's exactly what we're looking for. We're looking to match that diameter. So
another question. So, cameras and LiDARs emit observations at different rates. How do you account for that or match them up?
So that is through our temporal synchronization scheme. The Metrical init mode will actually calculate rough synchronization timings for each modality relative to each other. So for every pair of components, LiDAR to camera, LiDAR to LiDAR, camera to camera, blah, 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 you'll have a temporal synchronization group. It's not very sophisticated, but it really doesn't have to be. What we're looking for is the closest period between the two sensors. Right now, this does mean that we need accurate timestamps. However, what we're moving towards in the future is a continuous time adjustment. We're not going to get rid of Metrical as is. You're always going to have this static adjustment because it will be faster and more performant in those absolute timestamp cases. But if you're uncertain of your timestamps, we will have a mode to understand that uncertainty itself. So we'll have uncertainties in the metrics or in the components, in the space, and in time that you can then apply to a calibration. But long story short, most data sets have good timing. A lot of our customers use PTP or something along those lines once they introduce a camera or a LiDAR into the mix. So it's not too big a deal.
Okay, another question. How do I try this?
How do you try this? Metrical is a Docker image. I probably glossed over that because it just looks like a CLI. It is a CLI, but natively it's a Docker image that you just download. Talk to us to get a license key. It's a 30-day, we offer 30-day free trials, kind of no obligation. Try it out. Let us know if it's better than what you use today. And that's really it. That's all we expect. We're very high touch during trials. So if you have a problem or issue that you can't solve, just let us know. And we usually try and address it as fast as possible.
Any last questions? We'll wait another minute, just if anybody has any other requests or questions about Metrical or camera LiDAR.
But if not, I thank you all for joining today. I really do appreciate it. And hopefully it was informative. Even if you don't go forward to Metrical, I hope you learned a little bit about camera and LiDAR.
Yeah, and of course, if you think of any other questions afterwards, here we go. Here's a question. How do you automate this for multiple LiDAR camera combos?
It should be as easy as just running init. I mean, it really is. There's init. The init mode does a lot to auto detect what needs to be done. And so if you have multiple cameras and LiDARs, whether you run init once, if you want everything grouped, or if you run init multiple times, you really don't have to do much. It is automated. Init and Calibrate is really all you need.
Yeah, and I think I'd add a note.
For many of the poses of the circle pattern. Thank you. That is kind of what I was explaining with the logistics problem. So in some cases, you can automate this, right? You can have a robot arm move things around, or some of our customers have made sensor pods where you can kind of rotate that as well. But in some cases, you're just going to have to take a couple of data sets because, just because of spatial constraints, right? Things are just way too far away to get it all in the same data. Case,
what I would.
Oh, go ahead.
I was going to say what I would add to this is that you can have the targets be static and the device moving, or you can have the device be static and the targets moving. So when we set up Metrical on a production line, for instance, usually it's the device is static and the targets are moving with a robot arm. If we're setting up Metrical in a deployment environment, it's like a maintenance facility, we'll set up a target environment where a robot will come in and do a spin and get the necessary poses. In an R&D environment, when you just have a, you're not yet deploying fleets of robots. I think it's what Brandon's referring to, where you're going to do a manual process where you
That's right.
move around, and as long as we have overlapping observations of either the target or from camera to camera, we should be fine.
And I also want to emphasize on that, when we go into automated production lines, we don't just use one board most of the time. So one board is useful for quick evaluation, but, and I will caveat this by saying no one has quite used two boards yet. It hasn't been necessary, but there's no reason you couldn't use two boards of different diameters to get rid of ambiguity. And as long as your coding in the middle is different, you can probably use as many as you like. So that's why we have customers with, like 8 or 9 different targets. Not that we directed them to do that, but having 8 or 9 different targets on hand just gets rid of the ambiguity altogether. So a lot of different ways to do it. But it really is a case-by-case basis, depending on your size, like the room, your speed need, and who's running the production line.
Excellent. Well, we're slightly over time, but thank you everybody for joining today, and thank you for your questions. If you have any others that we didn't cover in this time, feel free to reach out to us at metrical@tangramvision.com. It'll go to us and other members of the team. Feel free to ping us on LinkedIn. We're at Tangram Vision, or Twitter/X. But yeah, happy to answer any questions that we didn't get to. Thank you everybody for joining. Have a great rest of the day.
Bye all.